right. And so I'm going to go ahead and put you on the main view here. There we go. So I know Eric from grad school. He went to undergrad at University of Virginia. Then we met each other at UCSB a long time ago, somewhere around 03, 05. And then did you go to Harvard or was it MIT after that? I forgot.
I did a postdoc at Harvard.
Right.
Yeah, and then came to Stanford.
Right. And so he does geophysics. He does a lot of computational physics. He knows a lot more about grad school these days than I do because I'm out of date. So why don't we, does anybody have, well, Eric, why don't we just start by having you very briefly talk about the kinds of things you work on and what your life is like?
Yeah. So, I was an undergrad physics major and then went to grad school in physics. And I thought I was going to do
hold on.
theory.
Wait, Eric, somebody wants to say hi.
I saw a little head poke in.
Hello.
Hey, good to see you.
Hello, friends.
Okay, I better get to it. He's got to get to work.
Okay,
Oh, you're going to say
bye-bye.
hello? Here. You can say hi too.
Hello.
Say
Hi,
to
good to see you.
Bye.
Okay,
Bye.
get back to work. All right, sorry about that.
Yeah, so I knew I always liked physics and then thought I would do string theory or particle physics because it was like the most fundamental thing out there. But I kind of got disillusioned with it in grad school. I really liked the math and I could do the math, but I was like, this is getting so abstract. Like, what's the purpose? Do I really want to, will this be a fulfilling career for me to pursue? So I almost quit grad school and became a high school physics teacher, which was something that I as being a TA in grad school, I realized that I did like. But then through some roundabout ways, I got introduced to some people in the earth science department who were working on earthquakes. And I grew up on the East Coast in Virginia, so I didn't really know what earthquakes were. But as I got into it, it turned out to be a really fascinating field. It's a problem that in a research area where I can get to do a lot of the fundamental math and physics and also computer programming that I really like to do. But I could also tell my parents about it and they would be like, that's really cool. You're doing something that's important for the world. So I've really found that fulfilling. So my work it started on earthquakes and I still do a lot with earthquake modeling. But I do other natural hazards like volcanoes, tsunamis, a little bit of work on ice sheets. But it's mostly fluid and solid mechanics, the kind of stuff that you would often get taught maybe a little bit in physics, but probably more in like engineering programs. What else can I say? Graduate school, so I'm in a geophysics department. Usually geophysics is just a smaller part of an earth sciences department at most universities. I don't know if it really makes too much of a difference. And I spend my time, maybe say probably a third of it teaching and then the other 2/3 doing research, which really means I do a little bit of research myself, but mostly it's working with students, graduate students. And I mainly work with PhD students, although I've worked with some master's students. And in our program, we recruit graduate students. It's usually about a 5 or 6 year experience. We pay you from the minute you get there. Not a huge amount of money, but certainly enough to live on, even here in the Bay Area. And you spend the first year or two doing classes, primarily, getting started a little bit in research. And then the last 3 years are much more like just a regular job where you're doing research, which for my students, that means solving equations, writing computer code software to solve those equations, then trying to connect it with real data from real earthquakes or real volcanoes. It's a long commitment, right? 5 or 6 years. So I think a lot of students, especially if they don't have like a family member that has gone through it and can vouch for it's an intense experience. It can be pretty fulfilling and fun. I think there's some reluctance there. Anyways, that's sort of a broad overview, and I'm happy to answer more questions that you have.
So students, you're welcome to ask any questions you want anytime. You could maybe just throw them in the chat And while you're thinking up your own questions, maybe I'll ask another one. I'm curious, Eric, are there any like kind of things that stand out to you when you're looking to hire a grad student or bring somebody in, or things attributes of people that you think help them be successful as a grad student?
There's sort of the technical skills, so I look at how students have done in what classes they've taken, right? So that, have you taken the right kind of math, calculus-based math classes? Have you done, or any calculus-based physics? Have you done some, in the case of my research group, this is not true for other research groups like experimental groups or field groups, have you done programming, that kind of thing? But at the same time, I also recognize that a lot of students may not have had the opportunity or didn't know that they wanted to go into this field. But geophysics is not something most people know about at the beginning or early on in their life, or sometimes ever, right? So, if someone has like a good solid background in engineering or in physics, but has never taken an earth science class, like I've still had very successful students come with that background. I think we're looking increasingly more at other attributes that, trying to gauge, how independent, how sort of intellectually curious you are, right? Because it is, especially the PhD, is a long commitment and requires you to become fairly independent in the latter stages. Again, that kind of depends on your advisor and how hands-on they are. And so, skills like perseverance and grit and, just a work ethic, you'll meet challenges, right? And you've met them in the past, right? How have you overcome them?
You've had to say like deal with a really, really big jerk for your Phys161 class. Oh, that's, yeah. I see a question from Christian here in the chat. He says, what was the most interesting undergraduate class you have taken?
What did I like best as an undergrad? It was still probably some of the mechanics classes. For some reason, I've always, by the way, I am a notoriously hard grader, so in common with Professor Joystad. Yeah, I think I always liked just the fundamental mechanics classes, right? They were always, I can always visualize them so well. I can see a mass, I can imagine a force, it moves, right? It begins accelerating. I've always been able to understand that and think about it a lot better than electricity and magnetism, for instance. So I can do all the math there, but I don't know, I can never really see these E and M, B and B fields and all that kind of stuff.
Yeah.
I'm
curious, at some point you must have kicked it into high gear with coding, right? When did you really start picking up coding? Was it like maybe junior, senior year? You took a CS class as an undergrad, or what happened?
So I'm in a geophysics department studying earthquakes, but I've never taken an earth science class. And I've only taken one numerical methods or programming class. In fact, I think I just audited it sort of later in grad school. Yeah, so it, I just picked up these skills because I realized that they might be important for the kind of work that I was doing, or that's sort of what how I encountered it, right? I had problems that I needed to solve. I didn't know how to solve them pencil and paper. I had to solve them, with some numerical method on the computer. And so I just, picked up the skills, got textbooks, got research, journal articles, found made the right connections to other people at UCSB who knew that and could teach me.
So,
but I wouldn't say that, nowadays I think there is much more of an appreciation that coding and programming and solving equations numerically is in many ways almost more standard than solving things analytically and doing theory and modeling, right? So I would encourage you to explore that if you have the opportunity.
Yeah, so like we just finished 6 weeks straight of coding simulations, right?
Mhm.
And just learning the basics, loops and stuff. So I'm hoping that wasn't a waste of their time. But I see a question from Angel here. Um, Obstacles you faced during college, etc., motivation focus wise. Uh,
I think it was less during college, right? College, I was like, each new physics class there, it just sort of opened the door to more and more fundamental things. The big challenge was that disillusionment phase that I went through, and it was probably towards the end of the first year of grad school, and continued for a while before I had founded, I found earth science and realized I could apply physics there. That was by far, I think, the biggest struggle. And then the other struggle kind of came as a young faculty member when, all of the responsibility for picking a research problem and a research direction rested on me, right? I no longer had a mentor or an advisor telling me, this is a pretty good area to work in, this is an interesting problem, oh, don't do that. Having that responsibility, and then actually having not only the responsibility for myself, but for my own students that I was recruiting.
Making sure you pick doable projects for them so they don't.
Yeah, exactly.
Yeah.
So it took me several years seeing that it actually did work out and my students were satisfied with the experience, right, to gain that confidence myself.
But so then I guess the summary was that you didn't really have huge obstacles during undergrad for you personally. It was more the grad school and beyond.
Mm-hmm.
Yeah. Okay. Seeing Esteban's here, I know you have to get going for an office hour at 1. So I wanted to see if we could get as many of these questions in. Esteban asked, is there anything you would change or advice to your younger self or advice for burnout?
The burnout one's important. And this is one that I talk with not just my students, but all the grad students at Stanford about. I think particularly at a place like Stanford, and I saw it before when I was at Harvard, right? There's this temptation to work all the time, because you will see people do that. Same as a junior faculty member, same as a senior faculty member, you'll see your colleagues, putting in crazy hours. And it can lead people to think that that's the only way to be successful. And I actually sort of almost crashed and burned and went through a depression as a postdoc, because this was at Harvard, and I was trying to do that, which is not something I did in grad school. In grad school, I had a really nice balance in my life. And then tried as a postdoc, I went to Harvard, I saw everyone doing this. I was like, maybe this is just what you do at this time of your life to be successful. And it didn't work at all. Like, I was not publishing, I was not going far, going anywhere in the research. And I kind of had this, it took a long time to sort of recognize that and realize I needed to delimit the time that I worked each day, put boundaries there, not work on the weekends. I bought a kayak and started going kayaking on the weekends. And suddenly I was happier. I was more creative and more productive. Everything sort of fell into place. And so I think the big lesson I learned there is that, especially when you're doing research, hard work is one side of it, and that's huge. And sometimes putting in longer hours, goes along with that. But there's another side to it, which is creativity. You can put in long hours, but it's not an important problem you're working on, or it's not an interesting way to solve the problem. Whereas if if you're in the right state of mind and you're creative, you can have this one idea that just, boom, you've got the solution, right? And it took you 10 minutes. So you kind of have to, I feel, find your own balance in your life that lets you remain satisfied and creative and avoid that burnout. Because, I did experience that. So cultivate your creativity and, take care of yourself mentally to be able to, have that sustained effort and creative effort. It's hugely important.
Gotcha. So I guess that would count as advice to your younger self, right? Yeah.
Absolutely. Yeah. I mean, if I could go back and tell myself that before I started the postdoc, I think I would have had a much better experience.
Yeah, I know this is unrelated, but I find when I go for a walk, I'm thinking about work, but it's a different way of thinking about it. You're thinking in broad strokes, and like I'm like, what can I do to most effectively achieve X or Y? And I think being outside, you think that way, you spread out and get creative, maybe. I don't know.
Yeah.
I see from Alexis here, what math did you need to study to get into geophysics?
Well, certainly calculus. The work I do involves a lot of differential equations, linear algebra, and then there's all the computational math. How do you solve equations numerically? And I guess you all have, it sounds like you all
We just do the Euler-Kromer method. That's the simplest one that I can.
Yeah, right. So, using those equations to integrate in time, using finite differences to approximate derivatives in space. I think that, there are some groups in geophysics that are more, let's say, lab-based or experimental-based, where the students, don't need to be the experts, in math, but at the same time, to understand why they're doing the experiments that they're doing, they do need to connect with the people doing the theory, and such. So some level of math is of course necessary.
I got you. So I see Christian has a question, but I want to sneak in here. So Eric, you've met multiple students from Hancock College, and you've had some students go up there and work.
Yeah, many fantastic ones.
Yeah, and I think a lot of students from Hancock probably have maybe an inferiority complex, where they maybe think that they're not competitive in a world market, an economy. But I mean, you could speak to that based off your experiences from what
I'll say that, right? So Stanford has an intern program where we recruit students. Well, we have two intern programs, one that has internal Stanford undergrads, and then another that recruits them from outside institutions. And I've had, I don't know how many, but multiple, maybe
about 5 or so.
Yeah, something like that. People come from Hancock, and they've been among the best, and maybe in one case, probably the best intern that I've worked with, on par with some of the students that came from Stanford, or came from other outside institutions. It's been just amazing to work with them.
So I think, I guess my thought process in bringing that up was, I want them to believe that if they're working hard like this here, I think they can succeed anywhere if they just, keep at it. And like you said, find balance, right?
I think that's true. Right. And recognize that, you don't have, it's not like you have to know everything going into graduate school, for example, right? I mean, it is graduate school for a reason. You spend the first 2 years taking classes for a reason, right? To build additional technical knowledge or whatever, in background and about earthquakes, background in math, background in programming or solving equations. And then you can be successful in the research side of it.
I got you. Yeah, I got you. I'm looking at Nick's, but so maybe you could get Christian's question, then you probably have to take off, Eric?
I haven't kept up at all with string theory, to be honest.
I did string theory too, right? We all thought it was the coolest, but it's like, I took the class, and I remember on the final exam, it just said solve for the a-hole. And I'm like, I can't take this, man. I'm out of here. Anyways, that was a weird final exam. That was an actual string theory concept, the a-hole, and I had to figure it out. I'm like, this sucks. So any other questions? Eric's got to get going here. We could maybe squeeze in one more, but he's got office hours coming. What do you think about fluids? We're doing fluids right now, and I tell them we're doing just the easiest fluids, like buoyant force and laminar flow, Bernoulli's equation, really basics. I tell them that fluids is really freaking hard, and that we don't know that much about it.
Any of these subjects can get really hard, right? There's always some. This was one of the most fascinating realizations, right? Is that there is a boundary to knowledge, and the purpose in grad school is to help you pick one area and bring you to that boundary of knowledge, and then you push it forward a bit more. So there are lots of unsolved problems, especially with fluids or solids. Those are the ones I know best. But at the same time, you all have the capabilities, with the right hard work and creativity to push those boundaries. So yeah, I mean, learn the basics, understand them, right? Unless you have that foundation, you can't go beyond that. And then look for it in the real world. That's at least what I found so fun. Like once I took classes in fluid mechanics in grad school. I took them the same quarter I took quantum field theory. Just night and day. I was like, I went to the beach in UCSB and I was like, oh my gosh, I can kind of see, the water surface is tilted. There's a pressure gradient pointing this way that's causing the fluid to accelerate. It's real. So that's what I've always loved about earth sciences or just mechanics in general. Like it's so, if you look for it, it's out there, right? So instead of keeping up with string theory, that's what I do. I want to learn about some new wave in the atmosphere or some new phenomenon like that. That's where I put my time and creative energy.
What's it like coding on those big mega computers, right? Don't you use like 1,000 cores at a time or something crazy like this? Or
yeah, we do everything from just MATLAB or Python on a laptop up to some big supercomputers where we're running on. One of my students is running simulations of earthquakes that are generating tsunamis, and then we also have the tsunamis in there now too. That was her research contribution where she pushed the boundary forward, doing that for the first time in 3D. She's running on several hundred nodes, each with, I forget if it's either 24 cores or 32 cores.
Wow, that's nuts.
Pretty cool.
That's got to be complicated trying to get those codes to work right and communicate with each other.
It's a giant team effort, right? So this is part of a big collaboration where there's multiple PhD students that are writing the code and doing all the optimization and getting it to work on these big machines, right? It's not trivial. And then there's students like my student who are more utilizing it to answer science questions.
Very cool.
Yeah. Anyways, I do have to.
Yeah, I'll let you go, Eric. Hey, thanks. Hey, thanks,
bit.
man. I really appreciate it.
Yeah, definitely. Feel free to contact me, any of you, if you have any questions.
All right, sounds good. See you, man. All right, everybody. So thanks for being patient there. Sorry if I asked him a lot of questions. Hopefully that was fun. So yeah. Any other comments about that or questions before we move on here? He's a nice guy. If you're interested, let me see if I can find it here. Come on now. So this is the program that we've been able, he's nice enough to basically, if I vouch for somebody, he'll at least take a look at their application. So and to be honest, right, with what he's doing, he does coding. So if you're an expert coder, that's what we can try to set you up with. And actually, he's taken one of my students, you know him, Ryan, Jose M. He's going to go up there, I think, this summer or work remotely this summer. So he still takes our students. Where'd you go, Ryan? What's up?
When you were solving for the a-hole for that final, did you write your name or no?
Yeah, the professor at the time calls me in. He's a world famous string theorist, right? Joe Polchinski. I don't know. You probably don't know him, but anyways, I go in. He's like, "Tell me straight up, are you going to do this or not?" And I'm like, "No way." He's like, "Fine, you get a B minus." I'm like, "Sweet, done." Because my work was not good on that one. It was so hard. It was so hard.
That's funny.
Yeah.
I'll stop harassing you now. All right.
No, that's good. I deserve it. All right. All right. So you're out of here. Oh, Ryan, do you have anything you want to address the class with here while they're all together?
No, that was
Or
cool.
Alexis, I saw Alexis somewhere. Yeah. Any advice you have for them? Because we're done with lecture pretty much. I got like 15 minutes and that's it.
Oh yeah. Okay.
Any advice for like Physics 163 from either of you guys? They've got Physics 163 with me in the fall.
Yeah.
How does it compare to 161?
Definitely harder. I heard. So I was always told this. I was always told Physics 163 is the hardest class you'll ever take, period. And
Was
go
that
into it with
true?
go into it with that mentality. In my opinion, 162 is harder, but I
Okay.
enjoyed 163 more.
Okay.
And so I just think that like whatever you enjoy more, like that's going to be easier for you because you'll be more interested in it. And that was my case. But I went into it and I was like, okay, this is going to be the hardest class. I got to work my butt off, which I did. I worked with others. You know, we all were like studying together and working as hard as we could. And because of that, like because we went into it with that mentality, I think it made it doable. And, you know, we were able to get through it and stuff.
How many hours a week were you spending? 10, 15?
Without including
Outside of
class
class. Outside of class.
probably around 10 or so.
Oh, that's what you're supposed to. That's
Yeah.
perfect.
Yeah.
All right.
Yeah.
So that's good. That means you can get an A doing what's recommended by. All right. So Ryan
Yeah.
accidentally just vouched for me. Yes. How about you, Alexis? Any comments you have? I know, Alexis, one of the things you did was you started in the summer, right?
Yeah, I started studying in the summer. I bought the well, I was gonna study with somebody else,
Mhm.
and I bought the workbook early, so
Mhm.
I just started doing problems. And one thing that definitely helped was having taken all Math 183 before taking the class, and just having that math background.
You were just stronger at the math required.
Yeah, and it just I don't know, the problems were all there, and to me it just seemed kind of fun. I'm just like,
Okay.
it's the summer, there's nothing, I didn't have much to do, so I just kept doing problems and problems,
I
and
got
I
you.
kept just going at it. There was a time during like the semester where I was just like, I don't want to keep doing this anymore, it's too much.
Yeah.
But I just kept doing it, and like I said, the background in math just made it a lot more fun. Any time where I was like, I can apply this from my class, like that always just brought a smile to my face, and it just made it worthwhile.
Were there any topics? I mean, I think chapter 13 that we just did looks a lot like, universal gravitation with the masses is a lot like and I feel like everything built off that. Was that a true statement or not? Or were there any easy chapters in there? What about the circuits?
The circuits were difficult.
They were.
But one thing that I always did was I always just kept trying to relate it to whatever math I knew. That's one thing that I always, like I said, it made it more interesting. And I was always like, trust the math and hope it takes me to the end.
I gotcha. How about you, Ryan? Any thoughts on that?
Yeah, there were definitely some harder chapters, some easier chapters. I enjoyed doing a lot of the circuits type chapters, and of course, your lovely problems that kill you.
Yes.
Yeah, the good ones. Just make sure you do those. Yeah, I mean, like challenge yourself with the class. That's what I would say. Instead of being like, oh, this is so hard, Jorstad's probably not going to put that on a test. Absolutely not. No, do the problem, right? So stuff like that. But I enjoyed doing that. The universal gravitation, absolutely. I mean, they copied each other's work, it seems like. I mean, it was just like almost exactly the same.
Would you guys say that my final exam questions are a little bit easier than the like quiz questions and like midterm questions?
Yes.
Yeah, right. It's sort of like, okay, you have to know more stuff, but I take the edge off the problems on the final so that they're more likely to succeed, right?
Yeah.
And even some of the quiz questions were, like you might even have taken a homework problem and made that a little bit easier just to be like, hey, did you understand the concept? Like, let's get through this,
Yeah.
Sometimes.
Yeah. I usually stick at least one on there that's just nasty as hell though, right?
Yeah.
But if you can identify which one's going to be horrible, then you can just be like, okay, focus on the rest of them, and you can still end up getting partial credit on that one at the end. And all right. Well, did you guys have any more thoughts before you take off? Or, I mean, you're welcome to stick around and hear 15 minutes of fluids, but you don't need to, obviously. So, or any other thoughts from Ryan or Alexis before you get out of here?
Enjoy your time with Jorstad. He's a great teacher.
Ha! I'll get you that $20 on Venmo later. Oh shoot, it's on mute.
Oh shoot.
No, my bad. All right. Thanks, man. All right,
Actually,
Alexis, you all good?
Yeah. I guess my last thought is those workbooks. I miss them.
Ah, it's good and bad, right? It's a lot of work, but you learn.
Yeah, I learned a lot of the physics from 163 from the workbook.
Yeah.
So yeah.
Right on. So, all right. Okay. So I'll catch you guys later. And class, maybe I'll do this right now. Well, I'll send you an email later, class, where I give you the links to all the 163 shit. So if you do want to start like the week before class or something, even, I don't know, did either of you guys, well, Alexis obviously did. Ryan, did you start like the week before class or not?
I tried a little bit of reading over the summer, and then when class kind of approached, I looked at more of the material. But I
Gotcha.
didn't do as much as I wanted to. But I
But
had
you
it.
had all your materials ready to go.
I
You knew where
did
they
have
were
all
and stuff.
the
Yeah.
material. Yeah.
Yeah. I think those little things can help, right? You're not messing around doing bullshit during the first week. You get right into learning during the first week. So you're ready to go. I think
Yeah,
that can
I
help.
really did hit the ground running. So it was helpful to, have that stuff so that you were prepared.
Yep. Yep. All right. All right. Okay. So let's take a look at some fluids really quick. And thanks to our guest speakers. All right. I feel bad. I kept yakking at Eric. All right. So give me a sec. We'll start with the screen share here. Oops. Come on, Zoom. So I just did FET, whoops, sorry. FET fluids to get this link, or you could see that link, just fluid pressure and flow FET. And we looked at this last time a little bit. Maybe it's going to do this. Sorry, it's taking so long here. I see my mouse doing something. There it goes. So I wanted to kind of review this before we go on here. All right. And so I think last time maybe I tried to do too much too fast. So let's just take a look at this one really quick. So let's start with this pipe, and fluid is flowing horizontally. We have some water flowing in, and these are shown by these black dots. So this is a laminar flow, right? Where the fluid's just flowing in a straight line. And now what happens if I turn on the friction? You can see that the dots at the top and the bottom at the edge of the pipe get slowed down. So what we are going to do is we're going to somehow assume we live in a magic world without friction. So our answers are only approximately valid here, right? So, all right, in this case, let's get these dots back on here. The first thing I want to talk about is obviously when we have this pipe just sitting here, let's get the fluid flow near the top. How about that? So we see these two things have the same speed. I'll measure the pressure near the bottom, just like pressure versus depth. You can see it depends a little bit. If I put the scale near the top versus at the bottom, there's a small change. Now, so maybe I'll put it right here and try and put it right about at 130, just so you see that they're both the same right now. All right. Now, keep in mind the numbers. What is atmospheric pressure? Does anybody remember atmospheric pressure? 1 ATM. What units was that? Or sorry, what is the number for pascals? Do you remember?
10 to the 5th.
Yeah.
Pascals.
Yep. And I'll put in the extra digits here just for posterity's sake. It's essentially 10 to the 5th, 1.013 times 10 to the 5th pascals. If we wanted to write that in kilopascals, whoops, 101.3 kilopascals. So that kind of gives you a reference for these units now. And we see that this pipe is slightly underground, so we might expect it should be a slightly higher pressure, right? So, all right, that's just the units there. And if we go all the way up to here, right, There's our number, atmospheric pressure. It's funny that it's changing a little bit. So they maybe even calculated in the effect associated with height, right? But so as we go below here in the fluid, we see that the pressure is a little bit higher because somewhere this pipe is probably open to air up at the surface. So maybe way off screen, you could imagine the pipe started over here. So the water was at atmospheric pressure at the opening of the pipe. And so now that we're down in it, it's at a higher pressure. All right. All right, so we'll see that. So now I'm going to constrict the middle of the pipe. And by that, I mean, I'm going to just shrink this a little bit. And I want to actually measure the pressure at the same height everywhere. So that means I got to move these sensors up a little bit. So what should be true about the pressure in the middle of the pipe there where it's constricted? What does your guess say? What should the pressure be in the middle of the pipe?
What kind of pressure are you talking about?
Ah, that's a good question. When a physicist says pressure, what do they mean?
Static.
Static pressure. That's what these gauges are measuring right here. They're measuring static pressure. So if I could, I'm going to draw a quick line here. You don't need to see it. That's just to help me line things up. So I'm going to move the pressure sensor over. Okay, I'm going to take this pressure sensor right here, and I'm going to move it over there towards the middle. It's going to be at exactly the same depth. So what should be true about the pressure? Do you think it's higher, lower, or the same as the scale reading on the left? So when I move this one over, what should happen to it?
Lower.
I don't know why.
I think the same.
This is here because I put
It's
Steven's
lower.
chicken on there. Why mix it
Now
together.
here's what's confusing. The speed goes up, but the pressure goes down. So what's the story here? The idea is this direction is the dynamic pressure, which is the letter Q, which is 1/2. Let me get rid of these dots for a second. Hold on. One half rho V squared. So notice if the speed goes up, Q goes up. Q is dynamic pressure. So that's a pressure in the direction of flow. Excuse me there. That's dynamic pressure. These pressure sensors do not read that. These pressure sensors are reading, let me see if I can move this on top here. So this pressure sensor is reading the static pressure. So this is reading capital P, which physicists just call pressure or static pressure. All right. So that's what that scale reading. And so if we look at the equation, Bernoulli's equation says P plus Q plus a density GH, basically a gravitational term, should equal a constant. So basically that entire quantity of pressure, dynamic pressure, and this gravitational term, that is constant. So what we're seeing in this case, if the H is a constant value, it's going to drop out on both sides of the equation. H1 equals H2. So the rho GH terms are going to drop out. So we see that if you constrict the flow by the continuity equation, which is A1 V1 equals A2 V2, by that continuity equation, if the cross-sectional area goes down, the speed goes up. If the speed goes up, Q goes up. If Q goes up, something else needs to give, and that is going to be the pressure, and it's going to drop. So far, so good with that. Any questions on this?
So technically speaking, when you have a hose and you're
Mhm.
constricting the water flow and
Mhm.
you're increasing Q, the pressure on the actual hose goes down.
That's right.
Wow.
Think about it this way. You're forcing the water to flow out more rapidly. So
Mhm.
you're increasing the amount of force it would take to stop the water stream. But that's because so much is going into kinetic energy. And that means, I like to think of it this way, even if it's sloppy. I say you're basically putting more energy into the direction of fluid flow, which leaves less energy perpendicular to that flow, which is one of the things static pressure is measuring. So if you crank up this kind of pressure, there's less for this kind pushing sideways. So you're increasing the amount of pressure you would need to stop it. That's called stagnation pressure. So if you put these two together, we're talking about the amount of pressure required to stop fluid flow. However, this only, P, is the amount of pressure that sensors measure. I don't know. Does that kind of make sense?
Yeah, it's sort of. So is pressure kind of related to energy in a way then?
Yes, this is an energy equation.
Mhm.
This is energy per unit volume. Now, if I show you this, let me go to the whiteboard. Okay. Let me get me up there. All right. Okay. So let's start with, we have kinetic energy plus gravitational energy plus work done equals K final plus U final. Did I show you this last time? I don't remember if I did. But I just want to point this out. This is a 1/2 mv initial squared plus mg height initial plus the work done equals some stuff. So far, so good. Let's focus on what work is. Work is equal to the integral of force dot ds. Now I'm going to just change that. Let's assume everything's in the x direction so I can get rid of the dot product and stuff. All right. So I'm just going to assume we're talking about a force in the x direction and we're talking about moving in the x direction. Okay. Just being a little bit lazy here. Well, this force is, I'll call it delta P times area. Right? Now think about that. This is a change in pressure. The net force on a fluid should be related to the pressure differential times the area. The difference in pressure times the area, right? If you have more pressure on one side than other, you remember Eric was saying, oh, I can look at the ocean and see the pressure gradient. That's basically saying I could see there's a high pressure region and a low pressure region, and there's a force from high to low. All right. So in this case, are you okay with this form of the equation?
Yeah.
So now I'm going to cheat and be lazy. Area times a length. Isn't that basically change in pressure times volume?
Yeah.
And in fact, this is how you could calculate work in an engine for an isovolumetric process. So if you're interested about physics 162 and engines and thermodynamics, this is an equation that will show up in that class. All right. Now, if I put that in here, I'm going to cheat. There's my equation. All right. So I've used the work is change in pressure times volume. And this would even work if the tube is changing shape and things like that. So that's cool, right? I was just lazy assuming it was only going in one direction. But now if I divide everything by the volume, over here, all the M's over V's become rho's. So it literally is exactly conservation of energy. And I know this may seem like a waste of time, but this is the one thing I want you to get out of this. We have made this quite painfully clear that this is a conservation of energy equation. That means conservation of energy rules apply. That's why this is a height, not a depth. So in this equation, this is height. It's an energy equation, it's height. And notice this here is going to be P final minus P initial. And so depending on how we want to look at this, all right, you could move this around, but basically there's two pressures here. So notice this is where we get pressure 1 and pressure 2 on the two sides of the equations. So I'll leave it at that. Esteban, does that address your question or not?
Yeah.
Yeah,
It makes sense.
straight up conservation of energy. All right. Okay. So now let's go back into, so I want you to keep that equation in mind when we look at this simulation one more time. So now what I'm going to do is I'm going to lower this side down and I'm going to raise this side up. All right. And so we're looking at the fluid flow near the top of the pipe. And so now I'm curious. I'm going to try and make this approximately the same diameter here. So in this case, it's not perfect. But if we look here, it's about 2 in 1 unit. This is kind of hard to see, so let me do this. It's not quite 2 in 1 unit. Pretty close. All right. Sorry if it's not perfect. So now in this case, remember, this is still flowing here, right? So I'm curious in this case, what do you think will be true about the pressure here and the speed if I put these gauges now over here at the right side, at the output? What do you think should be true about the speed? Do you think it'll get faster going downhill or not?
So you have more MGH, right? So
I like how you're talking about an energy equation. So I'm going to try and use the top of the pipe, kind of like right at this level. So we're comparing this. So, right, I could set this to H equals what? What would be a good number for that?
the bottom one,
Yeah.
H equals 0.
Yeah, the lowest point in the problem. And then based off this ruler here, just kind of eyeball it. Sorry, I'll get this out of the way. What do you think? Maybe like two meters or something?
Yeah,
for
we
the
could
other
say
one?
2. We could say 2.
It doesn't really matter. Okay, so notice we're specifying heights. Okay. So I know the different heights. So what's your gut tell you? If I just stick the speed sensor on there, we're at a greater depth or a lower height, however you want to think about it. Should the speed go up? What's your gut tell you?
Up.
Okay. What?
It's the same.
Why?
No.
The pipe doesn't explode. A1 V1 has to equal A2 V2. Otherwise, the pipe would explode or be leaking. That's the same thing as saying fluid in
Oh, I get it.
equals fluid out. So yeah, go ahead.
So velocity is directly related to the area of the pipe. And I was thinking that velocity is related to the energy equation.
It is.
So, but it doesn't, velocity doesn't change. If it's the same area, then it's going to be the same velocity.
Exactly. And so that means something else had to do the changing.
Right.
In the previous problem where we fell down, there was no pressure term. So, right, we're saying P1 plus Q1 plus rho G H1. And I'm going to call this one H1, and I'm going to call this one over here H2. All right. Now, over here, we've got pressure 2 plus Q2, dynamic pressure 2, plus rho G H2. So immediately we know something is the same on both sides in this scenario. If the areas are the same, what does that tell us about the speeds?
They're the same.
If the speeds are the same, which term in Bernoulli, P1, Q1, or rho g H1, is the same in state 2?
Q1.
So this is the same. Now
So
we can
P-
see H went down.
So P2 has to go up.
Exactly. So let's throw it in there. And so it's basically conservation of energy, but you have to, and this is essentially the same thing as pressure versus depth. So if the speed doesn't change, the pressure has to go up. If the pressure doesn't change, then the speed would have to go up. And that would mean, how could I make this so that the pressure stays the same? What could I do to the scenario to make the pressure stay the same instead of going up by 4 kilopascals? What would I have to do to the scenario physically?
You have to change the height.
Okay, I could change the height. That's one thing. What's something else I could do?
You could change the Q2 and that should lower the P2.
How could I change Q2?
Constrict it.
Aha. We're getting somewhere, right? It may not be enough, but maybe if I constrict it here too, right? So look, you could actually make the pressure drop if you constrict it enough. And so we'd have to get it at exactly the same spot, but you could see that this is a pretty complicated problem where it depends on. There we go. So if you get just the right constriction, I'm going to clear these things off of here for a second, just so you can see it a little bit better. We see now. Oh, go ahead.
I thought you meant but also keeping the same velocity. So that's why I was like, it has to be H.
Oh, I see what you're saying. Yeah. So if you wanted to keep the same velocity, you'd have to change H. If we weren't constrained by that, we could do all kinds of changes. But all right. The moral of the story is, instead of our simple gravitation and kinetic energy problems like a ball on a track, these problems are a little bit more complex because there's 3 parameters that can change. So obviously, in general, it's most common if all 3 parameters change: the height, the Q, and the P. However, we see that the sum of them is a constant. Now, again, this ignores friction. In the real world, friction obviously matters, but this will get you an idea of how things might happen. And this will probably give you a pretty good guess as to how much pressure would be in a pipe if you do all the plumbing. And that could tell you about how thick the pipes need to be so they don't burst. And then you could say, let's put in a safety factor, double it, just to make it even less likely to burst. Or do the minimum safety factor you can while still meeting or the maximum safety factor you can while still meeting your budget constraints. So this is the problem that infrastructure faces, right? We need to give ourselves maximum quality, but we have to pay for all these pipes and lines. And so you have to do some kind of optimization, and safety is usually what gives, right? You can't be perfectly safe all the time. Yeah, that's just a fact of life. All right. Questions on that? All right, let's look at one problem from the book and call it good. So I want you to open up to, whoops, I'm in the wrong chapter. We'll do this one together. 142. By the way, Esteban informed me that one of the problems on the homework quiz that was randomly selected was not in the assigned list. So if that happened to you, we could fix that after the fact. So I apologize if you were asked about one that wasn't on the required list. We could look at that later if that happened to you. All right, I'll just have you show me a problem in lab tomorrow or something. So if that happened to you, let me know. Okay, go to page 142. Page 142 in the workbook. I'm going to bring it up here. We started this one last time, but didn't have time to finish it. So we're going to finish it today, and then that's it. Sorry, I'm taking so long. I forgot to have it ready. No, I don't want volume 1. Ah! Sorry, I'm wasting your time here. Okay, got it. And what page did I say? 142. There we go. All right. So in this case, it's a very similar looking problem. If you want a visual on it, let me give you a visual. Oh, and I see there's a chat there. Ha! It's one book to rule them all. Yep. But you only have one volume. All right. So here's the deal. We could see, we have to be a little bit creative here. I just want to point out that here is, we're going to kind of, let me do this. Okay. So we've got this problem here where, sorry. We'll go right at the middle of the hole. There we go. And then I'm going to match the leakage and I'm going to open this up. All right. So the idea here is we have this hole that's leaking fluid. And right now, what I'm doing is I'm pouring in water at the same rate so that this water level at the top doesn't change. And I think we're told something like this is height H in the problem. Okay. And then in practice, what we're going to do is we're going to put in a hole that could vary at different heights. So the hole is going to be here at some location Y above the ground. Now in this picture, Y is equal to 0 right now, right? And so I want you to kind of ignore this stuff down here. Just pretend this black line right here is the ground. So right now we're starting with the simple case of Y equals 0. So let me do this really quick. Just pretend that flat line that I drew is the ground. So, and right now we're saying that Y is equal to 0. All right. Now up here, I don't know if you could see this very carefully. Do you agree that the top of this can is open to air? And maybe I could even just move this so you could, oh, whoops. Oh, shoot. There we go. The top of this can is open to air. If you see that, there's a little hole there. Based off that information, what do you think the pressure is right here at the water surface? What's the pressure?
1 atmosphere?
Yeah.
ATM?
Yeah. And I'm going to call it P0. Are you okay with that? P0 meaning 1 ATM. Let's just measure it, right? Okay. 1 ATM. Got it. All right. What should be the pressure of the water at this output stream? Give me a second. What's the pressure right here just after it leaves the hole? Do you think it's higher than, less than, or equal to P0? What's your gut?
Equal to?
Let's see. Now remember, there's a small change in height here. Do you see that? Look at this. As you go deeper, we see the pressure increasing. Keep in mind, oh, we'll get to that. But then when you get outside here, right, it's basically exposed to the atmosphere. So as soon as it's exposed to the atmosphere, its pressure must be equal to atmospheric. I like to say it this way, and I know you're ready to ask a question, Esteban. Give me just a second. The reason I like to think of it this way is if the pressure wasn't atmospheric, like let's say the pressure in the steam remained 150, this water would blow out and spray all over instead of making a nice clean stream. So if you see the water coming out in a single stream, well, we know that the surface of the water must have the same pressure as the air that surrounds it. Esteban, what were you going to ask?
I wasn't going to ask anything.
Oh, my bad. Okay,
No,
maybe it
you're
was
good.
somebody else. Okay, other questions? All right, so now look at this in here, right? At the surface, it's 1 ATM. It's going up, 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 up. And then as we follow it out, right as you get exposed to the air, the pressure changes dramatically. All right. So far, so good. Now, I want to talk about the apertures. Okay, so the holes. All right, so I'm going to call the diameter of that hole little d, right? So little d is literally this size here, the size of the water stream. The other diameter is the diameter between these two. That's big D. And I hope you agree that in this simulation, the large diameter, big D, is much, much larger than little d. It's like 10 times bigger, right? Okay. So let me ask you this. If I measure the speed of the fluid here, it's 12. How fast do you think the fluid is moving up here at the top? How fast is the fluid moving? Excuse me. Oh, come on, annotator. How fast is the fluid moving right in here near the top? What do you think?
So volume is area times or area times volume equals. So since the area is bigger, volume has to be smaller.
You mean speed?
I mean, yeah. Sorry.
Okay.
As the area is bigger, speed needs to be smaller.
What is the equation we could use for these areas? Assume it's a cylinder. Assume it's a circular hole.
Oh, pi r squared.
Which is diameter over 4 squared. Is everybody okay with where we're getting this equation from? We're assuming that the fluid coming in or the fluid leaving the top should be the fluid that's going out the hole, right? Right now we see this is matched. So check this out. I see the velocity at the top is equal to D over big D squared times V2. We know V2 is 12, but this diameter, the ratio of the diameters is about 10. So what should V1 be approximately if you had to guess? Assuming the ratio of diameters is about 10.
So 1% of V2?
1%, 100 times smaller, 0.12. Now, right now, whoops, let's measure that speed up there. It's not getting anything. You see that? So what I need to do right now is I need to turn the manual off and let's watch the speed. Oh, we can't see the speed at the top. It's not letting us. But I do want to point out, obviously, as the water level falls, the fluid speed changes. But if we do this, all right, in this case, we're right back to our initial conditions. It's approximately 10 times or 100 times smaller, the speed at the top. So if the ratio of diameters is 10, the speed at the top going downwards, basically, this water is going to move downwards at approximately 0.1 meters per second, 100 times smaller. I hope you agree. Well, let me just see. Does that make sense before we go on? That's a crucial point. Is everybody okay that we expect the speed of the top of the water column to be moving downwards, but very slow? Is that okay?
Yeah.
All right. Okay. So now let's think about this. If we get our Bernoulli's equation here, let's look at this scenario. We know area 1 V1 equals area 2 V2. From that, we found that pi diameter squared over 4 times velocity at the top should equal pi little diameter squared over 4 times velocity at the hole. So this is a V hole problem, very different than an A hole. So this is not string theory, this is fluids. All right, so we see that V at the top is diameter over diameter, quantity squared, speed at the hole. Great. And what we see is because D is much, much less than D, the velocity at the top is much, much less than the velocity at the hole. Cool. I'm going to now write Bernoulli's equation to go along with it. This equation is called the continuity equation. Fluid in equals fluid out. Meters cubed per second equals meters cubed per second. So now if I write Bernoulli's equation, pressure 1 plus, plus 1/2 rho velocity 1 squared plus rho g h1, etc. Got it. Now, when we were looking at our simulation, remind me, what was true about the two pressures? At the top and at the hole.
They're the same.
Yes, this was P naught and this was P naught. So do you agree that those two terms are going to drop out in this situation? All right. If we set the bottom of the container as 0, let me see if I could get to our picture now. Let's go to our workbook problem now. 142. I'm going to choose, just to keep this easy, why don't we call this height y, or the height equals 0? If that height is 0, what height should I use for the top? Of the water level.
Are we calling, well, using those variables would be h plus y.
I would say this is h. H. So I'm calling the very bottom 0.
Okay.
Now you could call the top h plus y, but then the bottom would be 0. Agreed, Esteban?
Are we considering the hole to be at 0? Or are we
I was considering the hole to be at y. Let me ask you that. Do you agree? You could either call this 0 and this h minus y, or I could call this y and that h, and shouldn't we get the same?
Yeah.
So you could set your, Esteban's setting his reference level at the hole, so the height of the hole would be 0. For Esteban, then, this height would be h minus y. Let me bring that up here. And it doesn't matter, right? You could set your reference level wherever. I think what Esteban was saying is, look, why don't I just call this height equals 0, and then the top becomes, and that's why we've got both labeled here. It just depends on how you feel like doing it. And then I was saying, I'm going to call this height 0, which makes the hole height equals y, and that makes the top height equals h. And it gives you the same math. Agreed? So let's go back to this. So depending on how you choose to do it, but we do see in the end, these two terms can be combined. I'm going to get back at h minus y. Esteban's is probably a little bit more smooth. So that's cool. All right. So check this out. We know that V top is going to be less than V hole. Look at this. This is squared. V squared is going to be much, 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 much. So said another way, this term is Q1, right? This term right here is Q1. It should be much, 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 much less than Q2. Right? Because it's already much, much less than. When you square it, you're much, 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 much less than. I just wanted to point out here, even if the size of the hole is about 3 times, it's still negligible. Meaning, let's say you have a 1 centimeter hole and a 3 centimeter opening at the top. It turns out this pressure term is negligible because you get a squared and then another squared. So somewhere about 3.16 is the ratio, and that's discussed in the workbook if you care. Anytime the diameter of the top is more than 3 times larger than the diameter of the hole, this assumption is valid. This term is negligible. If this term is negligible, let's figure out the speed. Solve for V2. Okay, if you work this around and solve for V2, what are we going to get? All right, this term is approximately 0 because of this. So now I get rho g h minus y. I'm just bringing this term over to get an h minus y equals 1/2 rho V2 squared. Density drops out, and we get 2gh. So in this case, where the pressures are held constant, it is a straight ball falls down distance h, ball picks up speed, square root of 2gh. Right? This is effectively dropping a rock from rest. If we look at our simulation here, whoops. It's basically saying the speed here is 0 and it falls distance h. So the speed at the output equals the square root of 2gh, where h, little h, is the distance fallen. Got it? So far, so good. Okay. And then in the real world, if there's not something there, we see that as the fluid gradually creeps downwards, you get a little bit less speed. So in civil engineering, we say there's a lower head, lower pressure on there, right? So we see that speed dropping, 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 and then eventually it's going to go to 0, right? All right, that's pretty good. Okay, so there's that. Now, let's go back to our question and see where we're at. We've talked about this. We've talked about this. How would I determine the horizontal distance traveled, people?
Kinematics.
Kinematics. Okay. So we know the speed coming out of the hole. What should I do? Other than actually get what I'm writing on the screen.
List the X direction and Y direction, what we know.
Delta X, V initial X, V initial Y. Whoops, sorry. Let's say V final X, A sub X, T, delta Y, V initial Y, V final Y, A sub Y, T. Give me something. Whoops, T is the same. What's A sub X?
Zero.
AY?
Negative G, or G, negative G.
Negative G. What's V initial Y?
Zero.
Nice. What's V initial X?
V hole.
V hole. Delta X, that's WTF. What's delta Y?
Negative Y.
Negative y, you got it. Cool, you caught that minus sign. Don't know it. What's v final x?
V whole.
V whole, because ax equals 0. Done. Agreed. Easy. You could crank this out in your sleep. So let me bring up the solution here. I'll let you kind of work that out while I bring up the solution really quick.
What about if you were trying to figure out how fast the tank will empty?
Yeah, we could discuss that in a minute. Give me just a sec, all right? We'll end with that. All right, and whoops, sorry, I'm slow here. What problem is this one?
$14.28.
28, thanks. Sorry about that. My book's over on the other side there. Okay, there we go. So this is all this stuff right here. So there's the time, and maybe there's a smarter way to do it, but it looks like I got the answer right here. So it's some crazy looking formula like that. There's different ways to write it. No big deal. Esteban's asking about the time for the tank to empty. How would you figure that out, Esteban?
Well, I saw that the speed changes, right? Because it's, and so energy.
Well, let me ask you this. Time for tank to empty. Let's say one of the things we could do is we could say, well, what directly relates to the amount of water in the tank changing per second? What variable?
I'm not sure I understand.
Rate, right? Rate 1 is equal to rate 2. That's the rate at which water is leaving,
right?
Which is area 2 times V2. Agreed? So we know that you could figure out V2 as a function of the height. From that, you could also figure out V1. And since the height is a function of V1, you could write a code that says, give me the height. Once I know the height, calculate V2. Once I know V2, calculate V1, increment over a small increment of time, change the height, right?
Yeah,
and that would be one way to do it.
Which is basically kinematics, but just splitting it up into really tiny pieces.
Yeah,
it's kind of like is a change in acceleration, but we consider it constant by splitting it up into infinite pieces. Yes. I was wondering if there was a simpler way.
Isn't that pretty simple?
Well, yeah, using coding, absolutely. But say like, so I don't know. I guess it just you're gonna shoot me with like some, I don't know,
you could do it with calculus magic, too, right? Couldn't you also figure out V2 as a function of H and then do calculus on it? It's the same, because the coding is doing calculus, right? When you cut it into little chunks, that is calculus. Go ahead, Gonzalo.
So yeah, I was thinking calculus, like, wouldn't we have to like take the derivative of like V with respect to T and then set it equal to 0 to figure out the time empty?
Well, that would relate to the time at which it's a maximum, which we know is going to be at T equals 0, right? So, but what you could do is we could work on this afterwards, but I promise we could look at this for just a second in office hours. We only have like 10 minutes left or 15. I'd like to do the next part, but for me, it's like screaming for you to code it because it's so easy to code it. Now, to be honest, you should be able to check that one using calculus. And isn't this a standard calculus question? In your
exactly. That's why I was bringing it up, because you do see it in calculus, and you could you could take the derivative. I know that, but I was like, I don't know. I just remember that you were saying something about that, and you're like, oh yeah, but as a physicist, you said something,
Mhm.
and I just can't remember what you said.
Yeah. Well, there's another one where you have this tank and the fluid's in here and you have to raise the fluid up to the surface and have it pour out, right?
Uh-huh.
And so in this one, I'm like, well, dude, just get the center of mass and calculate. Like they ask you how much work is required. Well, it's like, dude, just get the center mass and get MGH and you're done. You don't need to like.
That's probably what
That's
you
the one we
said.
were talking about.
Okay, I
Yeah,
thought it
yeah.
related to this one. Okay.
This one would. Yeah, I don't see any way you could do this without calculus.
Okay, I wish. All
All
right.
Well, here it is. It's
Yeah.
gonna be numerical calculus, and your answer would be great, and you could probably do this pretty quickly, and then you could do a lot with this that you couldn't do with regular calculus, because what if the shape of the vessel starts changing in some weird nonlinear way? You describe a function for it, it's easy. All right. So yeah,
Okay.
so I guess to be clear here, what you're doing is this is the change in volume with respect to time, and that might be what Gonzalo was saying.
Yeah.
So it's not the derivative of the speed with respect to time. He was saying dv/dt, and I think he's talking about volume with that v. Is that right,
Oh
Gonzalo?
yeah,
Yeah.
I was thinking DV.
Yeah, and volume is area times height. Well, I guess we're doing this now. All right. So area times height. And keep in mind, area could be a function of height as well, right? You could
Yeah.
have this be a non-cylindrical tank. So that equals A of the whole, area 2, times V2, right? And then we'd say, well, that's equal to area 2 times well, that's area. How about we just say it this way? That's also equal to area 1 V1, right?
Mm-hmm.
Now, assuming that A is a constant here, look what we derive back. V is dH/dt. That's just, yeah. All right. So I'd have to sit there and sit it down. I don't want to waste time on this right now because I wasn't ready for that question, but it's something like
okay.
this.
Yeah,
Right?
because I think the area. The thing is that the area is. Oh no! Wait, I'm sorry. No, you're right. Okay.
In this particular one,
anyways.
yeah. So it's not very interesting. It's basically saying you get a constant rate of change, which is equal. Yeah. So that's not very interesting. Yeah. More on that later. Okay. Obviously, let me rephrase. All right. Let's talk about that later. Let's go back to this one. Sorry, I just it's a fun problem. There it is. Okay. Here's the one that I wanted to talk about. A different calculus question. How would we figure out which height gives the maximum range for the fluid? So again, look at this picture. Let's say I'm going to drill a hole in here and I want the liquid to squirt out as far as possible. Any thoughts where we should put the hole? At the top of the tank, at the bottom of the tank? What do you think? Why do you say at the bottom?
Because there would be more of a volume of water on top kind of pushing it down.
And so what would become large if you put the hole all the way at the bottom? V2 would get large, right? There's a problem with that though. If you put it all the way exactly at the bottom, how far does it travel before it hits the ground?
Basically nowhere.
Basically nowhere. So we can't put it all the way at the ground. That's essentially like saying this. Oops, let me run this. Right? In this case, whoops. Let me get my line up here again. We're seeing right here, it falls below the line immediately if the hole is at the very bottom of the tank. Now, to be clear, the simulation I'm showing right now only makes sense if we consider the ground at this line that I'm drawing, right? So the problem I'm showing here, it falls away. That's a very different problem. But if we just consider how far will it go if the can is sitting on the ground? So if the ground was starting, whoops, let me do this. If that was the ground, we see it doesn't go anywhere, right? This thing is sitting on the ground now. So what if I put it at the top? What if I put the hole right here at the top?
It's gonna have very little velocity.
It's got a small time. What does it, if we put it up here, what advantage does putting the hole at the top have, or near the top?
It'll give it more height to travel more.
Yeah, it'll be in the air longer. So the trade-off is if you put the hole near the bottom, you get a lot of speed, but not a lot of hang time. If you put the hole near the top, you get a lot of hang time, but not a lot of speed. Take a guess what the sweet spot is.
Somewhere in the middle.
Somewhere in the middle. How would you figure it out? I want to maximize the horizontal position X by changing the height of the hole. How do I figure out the optimum height of the hole?
So you take the derivative
Of
X.
with respect to?
The height?
The height of the hole. What's the variable?
Y.
The height, y. So we're taking dx dy instead of dy dx. What? What do I do once I take that derivative?
Set it equal to 0.
Da, 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 da. Isn't that crazy? It turns out to be exactly right in the middle. All right, that's kind of fun. And you could see that these types of problems, even though they start out simple, just like Esteban's question, how long does it take the tank to drain, etc. So we see that there's a lot of different calculus questions that could come out of these simple problems too. All right, so let me see what else we got on this question to do. Let me see. All right, so now we've looked at this one. If you're curious, remember I said under what circumstances is it appropriate to say V top equals 0? Here's how I solved that. I just said, let's say I want the velocity at the top to be 1% of the hole. This is exactly what Esteban was saying a minute ago. He said, just say it's 1%. So I said the ratio of the diameters. Now, and then the idea is there's V squareds in there, right? So blah, 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 blah. It turns out it only has to be 3 times bigger for the fluid speed at the top to be negligible. All right. Let's go back to here now. What's going to be different if we angle it? How would our approach change if you angle this?
What are we angling?
If the hole was angled.
Oh. Then you would have some velocity in the y direction initially.
Yes. So that would look like this. Now, in this case, here's something kind of cool. Notice as I angle it, the max height changes, right? Where's the max height going to be if I shoot it straight up?
At like the water, was it like fill level? Or
Pretty much, yes. You see it? So it's not perfectly straight up. I just want to be able to see the difference, but we see that it goes essentially to the same level. It's just the kinematics problem in reverse, right? So I know that V here, the energy of the water at the top, if there's negligible horizontal, is 0. So it's all gravitational. So it shoots right back up to the same height. Remind me here, what's the velocity at max height in general? What's the velocity at max height?
0 in the y direction.
Is it 0 in general?
No.
No, there's some X component. So watch out for that. Is the acceleration 0 at max height?
No.
No, it's moving upwards right before, it's moving downwards right afterwards. The change in V is this way, just like we did with circular motion. A sub Y is negative G at the top. All right, just reminding you, it's kind of a review there. All right, so in this case, let's see, where else are we? I think we've finished this problem here. How would this change the problem? What if we sealed this thing at the top and maintained a pressure P1? Would anything be different?
Your energy equation, you would have
Yeah.
P1 on one side
And P0 on the other.
and P, yeah.
So it's a little uglier. All right, that's cool. So now we're done. Here's another variation on this one. I was driving into Pomo by the post office one time, and I saw this fire hydrant was blown out or something. I don't know if somebody drove over it or what, but I saw it squirting water up in the air about 3 meters tall. I'm like, I wonder how high, what does that tell me about the water main? So then I was like, oh, well, my students could tell me. So I wrote up this little problem here. And this would be another problem to just test your ability on all this. And I think if you do that, you know all the fluids you need to know for now. If you're curious, you can read about siphons. I sent some links about siphons before. They're really cool, but they're often misunderstood. And students a lot of times have very strong opinions about siphons, but turns out you should read and be careful when speaking about siphons. Siphons are more complex than people think.
So do you consider a straw a siphon?
No.
Right. So
not necessarily. I mean, if you bent it and turned it into a siphon, then yes.
Okay.
If you had a bendy straw, you could, in theory, make a bendy straw into a siphon.
Because I was thinking when I was watching that video you sent, I was like, when you because the outside pressures was causing you remove the inside pressure of the straw, so the outside pressure pushes the liquid up.
Yeah,
right.
But that's a different scenario.
That's what was getting.
So how does a straw work? Right? What do you have to do to drink fluid through a straw?
Well, I just said it. You empty out the pressure inside of the straw, and then the
how
outside
do you
pressure,
do that? How do you do that physically?
You inhale it or you suck it up.
So remember, there's no sucking in physics, just your grades. That's my fluids joke. Now you set me up perfect for it. So Gonzalo, this is physics, right? Now, the idea is you lower your diaphragm in the body. When you do that, you increase the volume inside of your body. When you increase the volume inside of your body with the same amount of air molecules, there's a decrease in pressure. The atmospheric pressure hasn't changed. It pushes the water up the straw into your mouth. Because you've created a low pressure region on the other side. There's a force from high pressure air into your got it.
And so that's why the size of a straw is limited by the amount of the pressure of the atmosphere. Yeah. Right. But then you have 50-foot trees that are able to bring water from their roots all the way to the top of the 50-foot tree.
How do they do it?
Exactly.
Do you know?
I kind of read about it.
I do because I'm the biologist.
Oh, how do they do it?
Well, that's a lot more complicated than you think. There's a lot of physics to it, but basically capillary action and very complex root systems.
Right. And does the capillaries have like a vacuum, right? I mean, that's the only way.
What's the lowest pressure you can get in a system?
0?
No, you can get negative pressure in a tree. Yeah. Hey, let me see if I got, okay. So class, we're done. I'm going to give you a video here just to show you this. I thought there was a pretty good one. I think it's Veritasium. I think it's this one. I'm not sure which one it was. I'm going to try this one. I've got 2 links here, so I'm not sure which it is. Sorry about that. And then everything's a physics machine. Everything. And then, oh, there's this really cool one. I think it's the bursting Pascal glass. Whoops, let me see if I can find it. Yeah, this is a cool one too. So there's an old experiment that's done where you take a container here. So the old story was that you used a wine barrel, right? And the wine barrel, there's like these two metal bands around here. Sorry, this picture is imperfect. Right. And the idea is there's a little valve here, and you take a hose and you stick it up on top of there, and you fill this thing with water. If you fill this thing with water, what happens to the pressure in the barrel? So let's assume this barrel is filled with water and there's a hose on top and you keep filling it. What should happen to the pressure inside?
You'd probably get a little bit higher.
A lot higher, because pressure depends on depth, regardless of how skinny the tube is.
Oh, okay.
So you could
That's
just take a
interesting.
hose, stick it on here, raise it up 30, 40 feet, and the barrel will explode as you fill it with water.
Really?
And then
So
the
that could
tricky
be
part is
that could even be a straw, the size of a straw? Like
yes,
something as small as that.
or Tygon tubing. That's the video, the last video I just sent.
Okay.
Now, the issue is if you try to do it, there's so much pressure, a lot of times the hose will snap loose before the barrel shatters. So you have to make sure you have really good gaskets so that the thing that explodes is actually what you want. And you watch that video, they fail the first time they try it. This is why, right, people like think they understand stuff, and then if you can't do anything with it physically, you don't really know anything, because you can't do anything. You might understand a concept, but if you can't build something and do something with it, I argue you don't really have a good knowledge. You can only kind of understand it. I don't know. That's just me. That's why I feel bad for you guys missing all the demos, right? Normally we do all this stuff.
I stopped pretending like I understand. I just rather be the clueless one and then just sit there and absorb, because
The more you learn, the more you realize you don't know, right?
yeah, for sure.
Doing chapter 14, I'm like, dude, I know nothing. So yeah, it's very, very difficult. The tree thing, it's very confusing to me.
Yeah, for
like
sure.
Gonzalo was saying, it's a tough problem, right?
So how do you get negative pressure? That's what I don't understand.
Well, yeah, and so that's part of this that is just weird. It's just a mathematical number, and so I'll let you watch the video and let you watch their explanation.
Okay.
At the end of the day, I'm like, you know what? I just like looking at trees. I don't care.
All
Sorry,
right.
my bad.
No,
But
you're
it's
good,
a pretty
you're good.
cool video, and you see all these physicists struggling with the same exact concept.
Yeah.
So physicists are notoriously bad at this chapter because they think they understand it. But like Eric, my friend from earlier, he really knows this stuff, right? And I know enough to know I am not good at it. And
Yeah.
if you're worried about it, that's usually a sign that you've learned something about it. I know that seems a